So I'm going to carry on where I left off and start with question 25. We have a falling ball with a velocity of 12.7 meters per second, passing a window of 4.81 meters above the ground. Now the question is ambiguous because the answer actually gives you the time from when it passes the window to the floor. And it's ambiguous in the sense that it actually looks like it's asking for the whole time. In reality, the question is much easier. So here's the information outlined, and because we're only interested in the second half of the journey, it's quite a straightforward calculation. We're going to use a quadratic form because we're going to use this equation in order to solve for t directly. So if we fill in the information that we do have, which is the displacement, which is the distance from the window to the floor, we have the initial velocity and the acceleration, we can see that what we're ending up with is a quadratic equation. We're going to bring that over here to give us its full quadratic form. Okay, so what I suggest you do is you just plug this into a quadratic solver and you find that the answer should be approximately, to the correct significant figures, 0.3 seconds. There is another solution, but it's a minus value, so you can discard it. Okay, so now we're going to try question 26. A ball is thrown vertically upwards with a speed of 18.5 from a window that is 12.5 meters above the ground. So let me sketch that out. Okay, so there are three stages, in fact, to this question, but it depends on what we need to look for. It rises, reaches its maximum point, drops to the same position, and then reaches the floor. Now the first part, A, asks when will it pass the same window moving down? So in that situation, we're going to consider this stage here. And I'm going to complete the table. So you can see our displacement is 0 because it's reaching the same point. Okay, so its total displacement from the original position is 0. The initial velocity is 18.5. Now the final velocity, this is important to take note, is the same magnitude because of course the same conditions apply, only in the negative. Here we have an acceleration which we've assigned as being positive because the direction this way, we are taking it as positive. And the reason we're taking it as positive is because we've written the initial velocity as positive. So that means this acceleration is positive and this one is negative. So if you have the same displacement up as you do down, the same acceleration but only in the negative, then your final velocity at this point will be the same as it was here. So these two will be the same. So your final velocity is 18.5, but it would be minus because now its direction is down. The acceleration we will assign as minus 9.81 and t is an unknown. So there are a number of ways to solve this, but this is probably the simplest. So I'll substitute the values in as follows. So you can see it's minus 18.5 equals 18.5 plus, oops, this is a mistake, so that should be minus 9.81. So t will equal minus 18.5 minus 18.5 over minus 9.81. So your value of t will be equal to 3.77 or 3.8 seconds. Right, part B, with what speed will it hit the ground? Now this is now considering the second half of the journey, or the third, because we had 3 stages, didn't we? So this is now the third part. So we have an initial velocity, which we worked out to be 18.5 things are much simpler now because everything's in the same direction. So we're just going to call everything positive now. Let's complete our table for this section. Okay, so you can see there we've got displacement, 12.7. Our initial velocity is now plus 18.5, because as I just mentioned, everything now is moving downwards, so we don't need pluses and minuses, and we have an acceleration of 9.81. So the simplest equation to use would be v squared equals u squared plus 2as, and it's very straightforward substitution of values. Okay, which will finally give you a value of 24.2 meters per second. Now part C seems a little bit more complicated, but it isn't. How far above the ground was the ball exactly after 2.6 seconds? So we don't know what we're dealing with now. We just know that it goes up and it comes down, and at some stage, at 2 seconds, it's somewhere along this journey. Now, in our first question, we found that it took 3.7 seconds to go up and down to here. So probably in 2 seconds, it's on its way down. But it's quite high up, isn't it? So if that's 3.7 seconds all the way up 3.7 seconds, then by second 2 it's probably about here somewhere. But we don't need to worry about that too much because the equations will kind of just find that position for us. So what we have to do is, again, complete SUVAT, but taking into consideration the direction, the fact that we have a plus and a minus, because we're going to be using values that are both in the upwards and the downwards directions. So our displacement is an unknown. Our initial velocity is 18.5. Positive, our final velocity, we don't know. Our acceleration is minus 9.81. And our t is 2. So we could just use s equals ut plus half at squared to find where s is. Okay, so by substituting all of those values in, we will get a value of 17.38 meters. Now that S is from the initial position. So we have 17 meters that way. But of course, it wants to know how far above the ground it is. So what you need to do now is add 17.38 plus 12.5 meters, which gives you a total of approximately 29.9 meters. Okay, so question 27. 2 balls are dropped from rest from the same height. If the second ball is released 0.750 seconds after the first, and assuming they do not hit the ground, how far apart are the 2 balls? So if we try and visualize it, although it's not easy, we've got a ball that falls for a certain time, and a second ball is dropped a little bit later. So we're going to call this 1 and 2. So the major difference here is that this time is going to be 0.5750, plus however long this takes to fall. So the second ball's time of flight is going to be 0.750 less than the first one. Okay, so we just need to present that in our table somehow. So let me do 2 little data tables, one for each ball. Okay, so we don't know what the displacement is, because that's actually what we've got to find out. The initial velocity is 0 for both. The final velocity, who knows? We don't know yet. 9.81 is the acceleration due to gravity. Now, for the first ball that falls first, we have 0.750 plus t, and t is the time of the second ball. Now, the question that's actually asked is, what is the distance difference 3 seconds after the second ball was dropped? So we're going to find S1 and then we're going to find S2. There is a difference in distance. Okay, so if we find this displacement and we find this displacement, we just have to subtract the second one from the first one to give us the value we're looking for, which is this. Okay, so we're going to use S equals ut plus half at squared for both. And because the first question is 3 seconds, basically we're going to replace that with 3, and that would be 3. Okay, so you just have to plug those values in now. The initial velocity for both is 0, so we can get rid of that bit. And then we just have a half a times 3.750, because you're adding these two up, squared. And then a half a 3 squared. Okay, so if we work this out, we should get 68.98 meters for the first ball, 44.14 for the second, and the difference between the two is 24.84. Now, for some reason, the book has a slightly different answer. It has 28.4. I think it might be a typing error because it's a bit of a coincidence that the 4 and the 8 have been swapped. But please let me know if you get the value that the book gives. Okay, then I'll look for my mistake. If you do get 24.8, send me a quick email because it will set my mind at rest. So that's question 27. Now B is exactly the same, but all we're doing is we're replacing the 3 here with a 5. And this would be 5. So it's a very, very similar process. For the second answer, you get 162.17, and for the other one you get 122.6 meters, okay, which gives you a difference of 39.54 abouts. Okay, so that would be for part B, 39.54. So question 28 is a similar one. A stone is dropped from rest at a height of 34 meters. Another stone is dropped downwards at 0.5 seconds later. If they both hit the ground at the same time, what was the initial velocity? So the difference here is they start at different times. Well, that's the same as the last question, obviously. But this one is thrown down, obviously, with some initial velocity, which we don't know because it lands at the same time. So that's really nice because we know that S is the same for both, and T, well, it's not the same time, I know I said that a second ago, but we do know something about the time. We know that the time for the journey for ball 1 is the same as the time for ball 2 plus 0.5. Like that. Okay, so that gives us something to play with. So what we're going to do is we're going to write the data table for both balls now. So we've got ball 1, okay, who has a displacement of 34 meters. Its initial velocity is 0. Its final velocity is who knows. 9.81 is its acceleration, and we're going to call its time t plus 0.5. Okay, so the ball 2, 34 meters again. Its initial velocity is what we're looking for, so we don't know. Final velocity is whatever, don't know. 9.81 is its acceleration, and this time its time is t, which happens to be 0.5 less than this one. Okay, so it's actually quite easy. All we're going to do is work out this value of time first. We're going to find t, the unknown t, using this data table because it's the most complete. And this is kind of what projectiles is going to be like, so it makes us think a little bit ahead. But let's find t using the standard equation, which gives us time when we don't have final velocity. So ut plus a half at squared, where will give us displacement. Ut is 0 because the initial velocity is 0. So if you just put in the values, 9.81 for acceleration, 0.5 for half, I don't know why I said that, and then s is 34. So rearrange that and you should get a value of t of 2.6 seconds. So from there, you now know what t is, because t is 2.6 minus 0.5, right? Because this one is 0.5 seconds less. So the value of this t is 2.1. So now we have a value of t. We can use exactly the same formula. We can use s equals ut plus half at squared. But this time we're solving for u. Okay, so we can write, I'll even write it in, 34 equals u times 2.1 plus a half times 9.81 times, oh, can't squeeze it in, 2.1 squared. So if you rearrange that, solve for u, you should get an answer for u equal to 5. Let me have a look at the significant figures. Right, so 5.9 meters per second. Now the answer in the book is 5.5. I'm not really sure why there's that discrepancy, but please let me know if that's what you get, or if you get 5.5 or 5.9, the same as me. Send me some feedback. Now let's try question 31, which is quite a fun one. We have a flea that accelerates at an enormous average rate of 150 meters per second squared during a vertical takeoff that lasts only 0.0012 seconds. What height will the flea reach? So we've got two stages. We've got the leaving of the ground and then the jumping. So you can say right from 0, its initial velocity of 0 to the point where its little legs leave the ground. It's got a final velocity, v. I thought it best to draw it in this direction, actually. So while it's still touching the floor, yes, that doesn't look like a flea, but I'm not even going to pretend to try and draw one. So while it's still touching the floor, it goes from 0 to a high final velocity in 0.0012 seconds, and it accelerates with this really high value. Okay, so we're not interested in that part of the journey. We're interested in the part of the journey where it goes up to its maximum height. But of course, in that, if we do the data table, we haven't really got much information. We know that acceleration would be minus 9.81. We don't know its initial velocity. We do know its final velocity is 0, but we don't know how long that time of the journey would take, and s is what we're trying to find. So what we do is we use the first table to give us the information that will allow us to work it out for the second part of the journey. So we want to find the initial velocity just when that flea leaves the floor, and that initial velocity is the same as the final velocity as it pushes up while it's still accelerating at this rate. So what we're going to do is use this part of the journey to then find the information for the second part of the journey. So what we're going to do is use equations of motion. Very simply, we're going to find v here using this equation, because we have everything we need. We have the acceleration, which is 1,500. We have the time, 0.0012 seconds, and our initial velocity is 0. So that should give you a final velocity of 1.8 meters per second. Now that can be put into this data table. And now we have enough information to work this out, because we can use the equation v squared equals u squared plus 2as. Now, why have I used a negative value here? Because my initial velocity up is positive, and the acceleration is acting down, and so it's minus. Right, so v squared, we substitute those values in. We have 1.8 squared, 2 times acceleration 9.81, and we need to find s. So if we put in all our values there, v of course is 0, we should end up with a value of approximately 17 centimeters. Now, this is a really cute question, actually, because now it asks you to measure how high you can jump vertically. So let's have a look how you would carry that question out. Let me tidy this page up. So if we think about this now, you jump up, okay, a certain distance, which the book uses an example distance of about 0.60 meters, 60 centimeters. So let's say this is your data table for you. We're going to assume that your initial velocity is really high, well, the highest it can be, but your final velocity is 0. Your total displacement is 0.6 as you jump up, and your acceleration minus 9.81. The time it takes, we don't know. So we have enough information actually to work out our acceleration. You can just use the equation v squared equals u squared plus 2as. Okay, we know our final velocity is 0. U squared we're solving for, plus 2 times minus 9.81 times 0.6 centimeters, or 0.6 meters. Okay, so if you solve for u, you'll get approximately 3.4 meters per second. But something like that. That's assuming you can jump only 60 centimeters. Maybe you could do more or less. Now the second part, the third part of this question, the second part of this you jumping situation, it tells you about bending your knees. It says in order to jump up, you have to bend your knees. Now use this information to calculate your acceleration. And that's because if you bend your knees, I'm trying to think, right, if this is your normal height, you bend your knees down to this height here. So let's say that's 30 centimeters. Bend your knees. These are your knees. And by the time, so when you're jumping, at that point where you just start to jump, your initial velocity is 0. By the time you stretch your knees out, you've given yourself the push you need, and your final velocity would have reached 3.4. By the time you're back to your normal height up here, you stop or you lose contact with the floor. That's when you actually start your jumping. That's when you begin this part of the journey. So by using this distance, you are working out the distance through which you are accelerating up to a maximum velocity of 3.4 from 0, okay? And so your data table for this part of the journey would look a little bit different. Okay, it would look like this. What is the displacement, or the distance that you cover while you are actually leaping in contact with the ground? Well, it would be 0.3 meters. What would your initial velocity be? 0. What will your final velocity be? 3.4. That's as your feet leave the ground. What's your acceleration? Well, we're trying to work that out. And how long does it take? Well, it doesn't matter. Because right now we have enough information. We have enough information to use v squared equals u squared plus 2as. So if you solve for this using our value for u, which is 0, 2 times acceleration, which we don't know, times 0.3. So if you solve for u, you should get a value of approximately 20 meters per second squared, which is about double the acceleration due to gravity. You could get something a little bit different, that's fine. Remember, this depends on what values you've worked out. So to find t, the duration of takeoff is using this data table, this situation, okay, and you can just use v equals u plus at using your new value of acceleration, which is 20 t plus your final velocity 3.4 minus your initial velocity, which is that. Okay, you should get approximately 0.2 seconds, depending on what your values were, but approximately 0.2 seconds.